The scientists that work in this space have been in this space for a long time, the ones that are producing really good science. And everything that exists out in space has to be science driven. And unless you're going to take the time to learn something about what it is that the scientists are doing in your company or in your organization, you're not going to be able to succeed. So cozy up to the scientists, try to get them to share with you as much as they can in layman's terms as quickly as they possibly can.
Hey everyone, thanks for listening to another episode of DIB Innovators. Today I'm speaking with Erik Ekwurzel, Chief Data and Information Officer at Slingshot Aerospace. Erik, thanks for chatting with me today.
Glad to be here.
Now, this is going to be fun. Love the space companies when they get on. There's so many cool things that are happening, but you're relatively new to the space industry. So talk to me about, your background, how you got, I perceive very much into the data side of technology and how that has then shaped to your current position, at Slingshot.
I'd be glad to. At the beginning of my career, I was pretty much jumping from startup to startup. So I was in a startup in the building industry. Then I joined a really cool startup in the medical device industry. They made little ultrasound scanners that you could scan people's veins and arteries pretty efficiently. And then in 94, I joined a startup in the business data industry up in Boston. And in 2001, Dun & Bradstreet purchased that startup. Dun & Bradstreet didn't really have a presence on the internet, so they gobbled us up. And just as I was getting ready to leave for another startup, Dun & Bradstreet offered me a role in 2004 to move down to the DC metro area and join a tiny division that Dun & Bradstreet had to build out facing the government, to build government products. And we built that tenfold. We grew that business about tenfold. And early last year, my former boss, Tim Solms, who became the CEO of Slingshot, he opened up this role in the middle of last summer, and I jumped at the opportunity. I love data. I spent a lot of time at Dun & Bradstreet. They manage massive amounts of business data. Figuring out how to manage data and apply it to use cases, especially in the government, is something that I really enjoy. And, I love data, and who doesn't love space? So it was a pretty super easy choice for me. That's how I ended up here.
That's great. Well, how does your, extensive experience in managing complex data, influence, how you look at space domain?
In the space domain, it is a data and analytics problem, and maybe I'm biased because I'm a data guy, right? But at the end of the day, you're essentially observing all these objects that are flying around the globe at breakneck speeds. And whether you're managing a commercial satellite or you're managing a satellite for the Department of Defense, and you're dealing with flying in and around and between and above other satellites, and more importantly, a growing amount of debris that's floating around out there, the only way that you can make informed decisions is to make data-based decisions. And the data that's coming from the sensors, it comes from sensors deployed in space, sensors deployed all around the globe. This is the data that enables you to determine whether or not your satellite is safe where it is. You need to make some type of operation to move it to a safer location, or do something with it that is closer to what your mission goals are. And all of that has to do with data. So when we think about Slingshot as a company, everyone at Slingshot thinks of as Slingshot as a data and analytics company. We could theoretically think of ourselves as a data gathering company because we have global sensors spread around the globe in 22 sites all around the world. So we do gather massive amounts of data. We could consider ourselves an artificial intelligence company. We could consider ourselves an astrodynamics company. But at the end of the day, what we're delivering to our customers is decision-valued data that helps them to make decisions one way or another.
Well, how you define your company is really based upon what the mission is. Are you trying to raise money, or are you trying to sell yourself to the government? different multipliers for different areas that you're raising money in.
That's certainly true for any startup. There's no question about that. You definitely would rather be a data and analytics / technology company than, say, just a straight up government contractor, because the multiples are so different. You're absolutely right about that.
So let's then just circle back for listeners that may not know, but Slingshot Aerospace mission is to
Slingshot Aerospace, here's the backdrop for that. There's 12,000 active satellites out there today, and there's an expectation that could be up to 100,000 by 2030. So space domain awareness is a real key element of national security, and Slingshot supports mission critical space domain awareness data, object behavior insights, and modeling and simulation tools. So we're making it possible to the best of our ability to allow our customers, in particular the government, to make sense of what's out there in space and to fuse that data and to make the best decisions based on that data. So we try to make space safe and sustainable for everybody that's out there in space, bottom line.
So for a knuckle dragon recovering fighter pilot, I guess I'll never get over that. But if we were to break this down, I mean, there is a ton of data, and we had this problem in the early days of drones collecting data. What do you do with all the data? How do you contextualize it? What is it? Where's the, kind of layer? What makes what you guys do with the data, and then how you're able to process it? What's the secret sauce in that? Is it your access to data, or how you then collect, contextualize, and process it?
Yeah, let me give you an example. So we developed artificial intelligence that's capable with DARPA, capable of detecting anomalous satellites in a massive constellation. And there's going to be more and more constellations. So it's really important to do that. But everybody out there should be asking, why Slingshot? Why is Slingshot increasingly trusted by the Department of Defense to train artificial intelligence, David? I mean, if you compare the size of our company to some of the huge defense contractors, you'd think they could just throw an army at these problems. And I'll tell you why Slingshot. First of all, we've built a physics true space training gym to train our AI. And in theory, anyone can do that. Anyone could build a physics true space training gym. But what makes ours produce AI that's so sought out by the DoD is that AI doesn't have to waste any time learning physics. And that's in the gym. And I'm not talking about just having a physics books in there per se. I'm talking about a physics engine that's been modified and tuned by our astrodynamic scientists who have built algorithms that they've worked with over years and deal with some of the nuances of space that are critical to a physics true space gem. So, how do you deal with a solar storm? How does that solar storm impact the drag on satellites based on the distance they are from the Earth? How do all of the various and sundry things that happen up in space impact what happens when a particular satellite kicks on a thruster? There's so much that goes into that making a physics true part of your gym is not child's play. And it's something that Slingshot does very well because we have such experienced astrodynamic scientists. The second part, which is probably even more important, is how much real data do you have inside of that physics, inside of that gym to train your artificial intelligence? And when you look at the landscape, there are 4 entities that generate massive amounts of observations, space observations, literally just measurements of things flying around in space. Bottom line, it's the United States, which has built up a global sensor and space sensor network over years and years and years. It's China, which is rapidly catching up to the United States and busy doing what China does. It's Russia, which has been trucking along and building a lot of space-based sensor capability. And then it's Slingshot. We generate over 1 billion observations every 6 months and about 8 to 10 million observations every single day. Nobody else in the commercial space does that. And when you take all of those observations plus the physics true gem, that allows us to build also massive amounts of synthetic data that goes into that gem that's based on that real data. So to build good synthetic data, which you need to train AI no matter what, you need to build some synthetic data. The more real data you have makes the synthetic data better. And so that gem is very good at producing very, very accurate and very powerful artificial intelligence. So that artificial intelligence that we built alongside DARPA is very good at assessing whether or not a particular satellite is not operating like the rest of the satellites. So the US government trusts Slingshot to build artificial intelligence leveraging our physics true space gym, space AI training gym. And in January, we were awarded a 1.9 million contract from the US Space Force, Space Systems Command, to further develop our existing jamming and spoofing detection capability. And that spoofing detection capability builds on a SBIRS Phase 2 contract by SpaceWorks that was awarded to us in 2021 to develop GPS jamming detection. Essentially, if you think of GPS jamming detection is all about finding out where people are, where usually malicious attacks are, to stop our GPS satellites from doing what they need to do to help ground forces do what they need to do. So the ground forces aren't essentially getting the right information from the GPS satellites, and then they're unable to function properly. And we're able to detect on the ground where that's coming from. Our new contract is to leverage artificial intelligence to further sharpen our capability to find and pinpoint exactly where those attacks are coming from.
Have you been able to use that operationally at all? I mean, I imagine with Ukraine and a lot of different, global hotspots, are you starting?
Yes, the U.S. Space Force is using the technology we developed in 2021 to help assess where jamming is taking place in the field of operations. And now they've asked us to, essentially we're being awarded this contract to further develop that work.
So you mentioned 4 big data collectors, if you will, the US, Russia, and then Slingshot was number 4. How do you get so much data? I mean, do you have your own platforms up there? I mean, have you guys launched
we have our own massive ground-based sensor network, optical sensors deployed all around the globe. And there's a difference between queuing, the sensors that you need to queue, and sensors that just stare at a large section of space. So if you think of a queuable sensor, that's a sensor where it might be a radar, it might be an optical telescope. You need to know where the object is and then tell the sensor to point at that object. So it's very good at dealing with what we call correlated tracks. These are objects where we know where they are and we know where they're going. If an object, like a particular object, satellite moves or thrust is used and it changes trajectory, sometimes it can get lost. Sometimes, if somebody in one country moves their satellite, another country doesn't know where it is anymore. It's hard to find it. You can try to point at it with a queuable sensor, but you might not find it. We have what we call staring arrays. These are essentially, we've developed technology that allows a bunch of sensors to stare at a large swath of sky at the same time. And those sensors, they don't move. They just sit there and stare at a large swath of the sky. So we've deployed those around the globe, and they see essentially the entire sky. Now, you either focus them at LEO or you focus them at GEO. We have ones focused at LEO and GEO. And they just stare. They stare at that domain. And when they see objects go across, an object flies across that, they don't need to move to see it. That information then just gets uploaded into our systems. We then use technology to fuse that data. And if it's a new object, it's called an uncorrelated track. If it's an existing object that we know where it was yesterday and we're just confirming where it was today, that's a correlated track. We're just getting a new observation on that particular object. If it's an object that we haven't seen before, then we work to put that in our space catalog, essentially Slingshot space catalog, and we correlate the uncorrelated track. We resolve the uncorrelated track. And to do that really well, you need these staring array sensors, and we have them deployed all around the globe.
I know you may not know this as you're relatively new, but I bet this business case was fascinating to raise capital on. We're going to invest, had to be tens of millions at least, to build all these arrays, to go get data. And then your real, business case is, now that we have the data, we're going to, process it and, make it actionable better than anyone else.
Well, I'm glad you asked that, actually. And this is, I don't know if this is on the record or off the record. Our cost for building optical sensors is an order of magnitude lower than the cost to build, say, a radar sensor. So if you build out a radars, you're talking about typically a football field sized area. And you're talking about a huge amount of power that's has to be drained, so you can't necessarily put it in some remote parts of the globe. And it's an expensive endeavor. These optical sensors that we've developed, we've invested a lot of time and money in perfecting them to do what they do, but they're sub-$1 million systems that we're able to deploy. And they do a very good job of not only knowing where an object is going, they are also a very good job of essentially picking up light, little bits of light that tell it a little bit about whether or not the object is spinning out of control or which way the object is facing. We call that photometric data. So it collects both astrometric data, where the object's going, and photometric data, what the object might be doing. Whereas when you're dealing with other types of sensors like a radar, you can pick up astrometric data, but not so easily photometric data. And that's the difference.
How big is the footprint of this array or this antenna?
Oh, one particular sensor?
Yeah, like if you go to a location.
Yeah, the sensor that is completely designed and houses itself. Think of a pad which is maybe 3 by 3 feet, and a pole that's about 6 feet to 8 feet high. And on top of it is the 8 sensors that are carefully covered in a housing that goes up and down depending on the weather. And that whole thing is probably 4 to 5 feet in diameter by 2 to 3 feet in height. Very small.
Yeah.
Now we have other sensors that are cued sensors that stand up about 12 feet, 8 to 12 feet, and you need to put a house around them like a dome that opens up and closes. And that's a little bit bigger, but the sensor itself is still relatively small. And the power that's needed for some of these sensors is very low. It's very low amount of power.
What type of sensor is this?
These are optical sensors.
So optical. And so weather affects it. You can't see through the weather. Day, night, does that affect it? Or
weather affects it. We have a patent in being able to see during the day. We use different modalities to see during the day. Not all of our sensors see in the day, but a lot of our cued sensors we've developed to see during the day, and we're looking to apply those technologies for some of our other sensors to increase the visitation rate.
What's the smallest object you can see in? And it probably matters on which orbit. I'm guessing, maybe not, but what is that? If you can share the smallest item.
The sensors can be tuned to what they need. It's more of a question in some cases about what we've tuned our sensors to see. So we've tuned our sensors to see, things in some cases down to a CubeSat or down to a bus, like something the size of more typically we're going to pick up things that are, when you're talking about 95% of the satellites that are out there, these are satellites that are typically a little smaller than, say, a dishwasher or something like that. That's the stuff that we're tracking regularly. But we are seeing objects smaller than that. We're not seeing stuff much below a CubeSat.
Interesting. Is there a specific orbit, I imagine, that you guys are focused on, or it really doesn't matter?
We focus on 4 domains right now, everything from LEO through cislunar, all the way up.
From an AI perspective, I'm not an AI guru by any means. So with DARPA, you created your own language model, or are you using someone's language model and then modified it to process the AI? What does that look like?
Yeah, so we're agnostic to what language models we're using. We are constantly testing various language models to see how well they perform, and which ones produce the results we're looking for them to produce. If you ask me what language model, I'd have to go back to to some of our scientists to give you a catalog of the ones they've used most recently. I think probably a good analogy for anybody who thinks about how these things are being trained inside of our physics truth, training gym, is you can kind of go back to these articles about Go, when Go started beating the best players in the world. And in the morning, you would essentially give the artificial intelligence the rules of how Go functions and the objective of the game of Go. And in the morning, quote unquote, in the morning, you would give it the rules and the objectives. That's parallel to the physics true portion of the gym. So AI doesn't have to learn Go. It has that built in, so it doesn't have to learn physics. And then you essentially, with Go, you have the AI play against itself over and over and over and over again, where it's using typically reinforcement learning, where it's being reinforced for winning and not being reinforced for losing, until you reach a point where you then take out one of the sides and you say, okay, I'm just going to have a human being play against you and see how you fare. And artificial intelligence can get very good at Go very, very quickly. I am dramatically oversimplifying what we do with artificial intelligence, but imagine a situation where you're essentially, the artificial intelligence doesn't have to learn the physics, and you're using either, using some type of learning methodology with that artificial intelligence to train it to, in this case, look for anomalies in a constellation.
So effectively, you're creating like an application layer. I mean, very intense application layer, but that's where you're working. You're not in the development of the, like you said, the model, the learning model, if you will, the LLM.
Right. We're not creating artificial intelligence. We're leveraging models and testing which models are producing the best results. That's right. That's exactly right.
And so as you look forward, you've got, correct me if I'm wrong, you have both public and private sector customers.
Yes, we do.
And so what's the difference there, and how do you balance, working with those different customers? Are the demands the same, or?
They're not the same. So for private operators, they're doing some of the same things. So let's be clear about that. When you're talking about private operators are managing satellites that are usually doing something that generates revenue for the company that owns the satellite. And they typically will have a space operations center, just like the government has space operations centers to manage their assets in space. And the Space Operations Center essentially has people, and those people's jobs are to fly the satellite, basically. And there's so much that goes into flying a satellite. There's avoiding collisions. That's a growing concern for satellites as space becomes more contested and congested. There's also things like just powering up the satellite by pointing the solar panels to the sun. There's making sure that the satellites, if you have a constellation of 5 or 10 satellites, that they're properly distributed in a way that collects the maximum amount of information that you're trying to collect, or whatever it is that the mission is for that satellite. There's all types of operations that you need to do day in and day out to make sure your satellite is doing what it's supposed to do to make money for you. And if you look at today's environment, the average amount of money that the average commercial operator is spending is about $909,000 per year to operate a satellite. That's the cost. And that cost is going to go up as space becomes more congested and more contested. It's just something that's harder and harder to do. It's, think of planes flying around the sky, and you have air traffic controllers, and the more planes there are, the more air traffic controllers you need. It just becomes harder and harder and harder to do. Well, in space, that's an exponential problem. So space operators buy essentially data from companies like ours in order to do mission planning, and they buy data from companies like ours to determine whether or not there's other objects that they need to be concerned about if they're going to make a maneuver in space. And we are looking to provide them with better and better information and more information driven by artificial intelligence to essentially help them do their job. That's our commercial.
Yeah. So I'm an operator and I go, I want to move this X% somewhere else. I don't know how they measure moving something in space.
Yeah.
Want to move to a different orbit. Let's just call it that way. They would contract with you and you just supply the data set, and then they've got to apply it into their system to harness that knowledge. Or are you producing data that's actionable so that they have that information right away and can identify, for example, when and where they should go to avoid collisions, let's say, other debris?
Yeah. So to the extent that they're willing to accept a recommendation from us, we will offer that to them in some cases. In today's market, in the space operations market, their primary interest is to just get data in order to make decisions. It's to get data to make decisions. It's usually space domain awareness data and space situational awareness data in order to make more informed decisions. And that's where the market is today.
But like on the government side, let's say the GPS jamming use case you talked about, they're looking for the output of the data to know where they're being jammed, not necessarily the data itself. So you are then delivering actionable intelligence, if you will, by just some terabytes of data that they then have to process.
That's right. And the other thing we're doing for the government is, we build our technology so that it's agnostic to what sensor data comes into it. So the government's more than welcome to deploy our artificial intelligence in their environment and feed it with, it's trained by us, trained in our environment, trained inside of our gym, but bring it into their environment, the finished artificial intelligence capability, and then feed it with data from their sensor, from the United States government's global sensor network, and then allow that artificial intelligence to tell the US government when a particular satellite in a particular constellation of interest is acting abnormally that they may be concerned about.
Yeah, so you don't have, the only data you guys process is the data you're collecting, yet you have the ability to give your AI tooling, to someone else to use, the government. Do you also sell your data then to the government so they can incorporate what you see? Are there overlapping capability sets of what they have? What?
We process our data, and we also leverage data that is provided by the government, and also data that's provided by other third parties to the government that then the government subcontracts to us to process for them. So we use our data fusion technology as well to make sense of a lot of data that not only comes from us, but also comes from the government and comes from third parties on behalf of the government. We also sell our artificial intelligence to the government that enables the government to observe the things that we're able to observe, both when it comes to things like watching a constellation and finding a satellite that's acting abnormally, or ultimately the types of technologies that we're building to watch for GPS spoofing, for example.
What do you foresee, or what are the biggest challenges in both collecting the data as well as processing the data that you see right now?
Data accuracy. So if you think about, this is not just a problem for us, it's a problem for the government, it's a problem for everybody. Just from the astrodynamics level, these objects are flying incredibly fast, 28,000 kilometers per hour. They're flying, they're moving. So everybody wants to know, by the time you see where an object is, it's already gone, it's somewhere else. And so you really want to know where it's going to be 8 hours from now, 16 hours from now, 24 hours from now. And there's a degree of probability of degree of accuracy that you have to put towards any measurement. So where's this object that's flying through space? Where's it going to be on Tuesday morning at 6 o'clock when I may want to intercept it because I want to do some reconnaissance, or I may want to avoid having my satellite hit it, or whatever reason I'm concerned about where that object is on Tuesday at 6 o'clock. I need to be able to project as accurately as possible based on where it is and the information I have on it, and make some assumptions about whether or not anybody's going to exert some fuel to move it between now and 6 o'clock on Tuesday. But on the assumption that no one's going to actually exert pressure on it, I need to figure out where it's going to be. That's a pretty complicated physics problem, and we're really good at that. And we're constantly working to be better at that. We want to be ahead of our competition. That's a critical part of this whole thing. So our astrodynamics scientists are constantly working to figure out, well, there might be, like I said before, a solar storm that happens between now and Tuesday at 6 a.m. So how's that going to impact the trajectory of that object, and how do we factor in for those types of things? The second is the time it takes from an observation from a sensor that's sitting in Africa to it being available through an API to one of our customers. That's in my domain, uptime and latency. So our scientists are working on accuracy of measurements and how much insight our artificial intelligence drives for our customers, our government customers and our commercial customers. And my organization's focused on making sure that all the plumbing is up 99.9999 plus percent of the time. And the time that the observations take place, coming all the way from Africa, getting all the way into the cloud, going through the data fusion technology to make sense of what those objects are, going through the technology which determines the orbit determinations and all of the astrodynamics, any artificial intelligence that has to be applied to it, and then it needs to be delivered to an API to a customer. We're looking to make that as small as humanly possible so that there's almost no latency, if you would say. So those are the types of things that my side of the house is working on, and then the scientists are working on the accuracy side. We work very closely hand in hand because both sides of the house of these organizations, the science organization and the data management organization, we have to deliver our capabilities. Not only do I need to be synced with the head of that organization, Belinda Marchand, and I talk to her at least 2 to 3 times a day. Everybody throughout my organization, all of the engineers and all of the ETL specialists, ML ops, all those people need to be closely synchronized with all of the scientists that are doing the work on the algorithms in order for all of this to move forward as an organization. And I'm kind of getting into how these organizations work, but in order for us to work such that both sides, you get into some situations where if you let the scientists try to work on uptime and latency, they might not be the right ones who have those skills. And you certainly can't let software engineers trying to do science. They'd have no idea how to do that. So it's a really interesting balancing act to actually produce a quality product in this space.
Very true, I'm sure. Well, what are the biggest trends you believe in, space data analytics over the next 5 to 10 years?
The biggest trends?
Yeah.
The U.S. government has stated this more than once. And the biggest trend for sure, and we've been talking about Slingshot's ability to produce AI almost this entire interview. So this is going to sound like it's aggrandizing or something. But for sure, space is getting too complicated for people to manage satellites indefinitely. It's just getting crazy up there. There's 12,000 satellites today. Imagine a world where there's 50,000 satellites, 100,000 satellites. It's an exponential problem. If your average satellite has to move just to avoid a collision, X times a year, it's going to be, 10X, 100X in 5 years. So teams of people saying, oh my goodness, we need to move our satellite. And then a day later, oh my goodness, we need to move our satellite. And then a day later. So you need to apply artificial intelligence to these things. Whether there's a human in the loop where you're having an artificial intelligence say, your satellite's going to hit another satellite or be hit by a piece of debris, and here's what I recommend you do, and you make the final sign off, or whether or not you ultimately have artificial intelligence manage satellites. It's the same issue. It's trying to do this without artificial intelligence is becoming untenable, and Slingshot intends to be there to address that need as it arises, frankly.
What do you see are the biggest challenges for the DIB and in this arena?
In the space arena, yeah. So intellectual property rights. So I began to notice this issue, which didn't exist in other arenas, specifically for, potentially you could call out the portions or it might be a cultural thing. I'm not sure what it is, but I watched in a lawyer engaged government and basically posit, if you don't begin to understand that the commercial sector needs to maintain intellectual property rights, then you're not going to be able to leverage the commercial sector as much as you would like to leverage the commercial sector. And how I interpreted what he was saying is something that we come across. So sometimes when we say we have some intellectual property, it might be our ability to fuse data to do orbit determinations. And we have some of the world's best that we've done bake-offs with against legacy government technology and other technologies. or we've built this artificial intelligence that I described earlier that can see minute changes inside of large constellations to determine if a particular satellite might be up to some nefarious act or doing something that's unexpected. When we sometimes engage the government in licensing those technologies, sometimes what we hear back is, I don't want to license it, I want to buy it. And that's a hard proposition, right? So if you do the calculus, say, well, if you want to buy it for perpetual use by the government indefinitely, then it's going to be an order of magnitude more expensive. And then the response is typically, well, that's way too expensive. I want to buy it, but I want to buy it at the price that you were going to license it to me. And it's like, well, wait a second. So there is, I don't want to point fingers, but there is one contract that I know about. And I won't say who the company was or who the buyer was in the government, but essentially the government's primary issue with that technology was that the technology was licensed to them. And they said, well, we no longer are comfortable with this, so we're going to hire a company to build that same technology for us, even though the built technology doesn't do as good a job as the licensed technology. And this isn't something that I saw when I worked for Dun & Bradstreet in selling intellectual property to the government. You know, think of an algorithm that determines a business's credit worthiness. I never ever had someone in the government say, I want to buy the algorithm from Dun & Bradstreet that determines the credit worthiness of a business. They were more than happy to license the output of that algorithm. It feels like in the space arena, I was almost taken aback by how many times the government says, I don't want to license your technology, I want to buy it from you. And that's a big issue, I think, for this sector.
Yeah, it's fascinating. Have the small business, pay them a little bit, get them going, and they're like, no, I just want to buy it, so I don't have to pay anymore. And you can't scale. You're gone.
Right.
That definitely is a challenge. Okay. Well, that's great. Well, I would say, last thing, if you give one piece of advice to, professionals or companies look to get into the space industry as you've made this transition, from commercial side to space, what have you recognized or what lessons learned would you offer to share with them?
One thing I did, I don't know, I mean, anybody who wants to get into this new field, and maybe this is true for moving from one field to another, but it's definitely true in this arena. When I joined Slingshot, I practically begged everybody day in and day out, anytime I was in any kind of situation where I was talking to the entire organization, especially, please throw a half hour to an hour on my calendar just to have a one-on-one. And in those conversations, I really did my level best to learn as much as I could about this domain, because this domain is a complicated domain. It's not a simple domain. And you could say that about other domains as well, but I think it's especially true here. I mean, the scientists that work in this space have been in this space for a long time, the ones that are producing really good science, and everything that exists out in space has to be science driven. And unless you're going to take the time to learn something about what it is that the scientists are doing in your company or in your organization, you're not going to be able to succeed. So cozy up to the scientists, try to get them to share with you as much as they can in layman's terms as quickly as they possibly can. That's my one piece of advice for anybody who's entering into the space industry.
Did the scientists want to sit down with you to talk about data?
They did. I mean, it's an interesting thing. How data is managed is not necessarily something that scientists think about. They know it's critical and they know they have to have access to data, but how data is managed in a secure way, how you perform science in a way that makes sure that the data remains secure while you're taking scientific actions on it. Once you've completed the science, how you move from demonstration of capability to delivery of a repeatable product in where the product is available 99.99% of the time, and the data gets converted by the algorithm near instantaneously. These are things that scientists want to know about, but they don't necessarily know how to do that. That's much more of a software ML ops, ETL engineering problem. How do you highly parallelize, as one of the people who works with me using the data and sort of the data engineering team, how do you highly parallelize something such that if 10 million observations come in, all of them flow through and get processed near instantaneously? It's a fascinating problem. And as you grow to 30 million observations and 50 million observations, and that's squarely a data problem, and it's not necessarily a science problem.
That's fantastic. Well, Erik, this has been fun. Unfortunately, we have to wrap this up, but if folks want to watch what you guys are doing, any big announcements that might come out in the future, how best would they do that?
Oh my goodness. They should come back to your channel, and they should, because you're going to be interviewing us hopefully again when we do that big release of another really cool piece of artificial intelligence, bespoke and ready to do what it's supposed to do for the government. We do our level best to be in a lot of the trade journals and to do our announcements. So I would say it actually be, if you read any of the trade journals related to space, it'd be hard to miss us, frankly. I'll be pretty clear about that. Our PR engine is pretty robust.
Well, that's fantastic. Well, I really enjoyed it, learned a lot. I look forward to having you on again. So make sure to hit me up when that announcement comes out. We'll do our best to get you on. And I have learned a ton. This was super fascinating. So thank you for your time.
Thank you.